In this lesson, we are going to look at geometric series. So mainly, we're going to determine when a geometric series exists and evaluate its sum if possible. So first off, partial sums of geometric series always exist. And so the nth partial sum is given by the following formula, Sn, where n is the number of terms that are being added, is equal to a1, the first term, times 1 minus the common ratio to the power of n. Notice that the exponent is inside the parentheses, not outside the parentheses, all divided by 1 minus the common ratio. And so let's do a couple examples of using this formula. So let me make sure I've got my pen tool. So the things we need for all of these are the first term and the common ratio. So the first term we find by plugging in 1, because our first term starts at n equals 1. So we have 2 to the power of 1 minus 1, 2 to the power of 0, which itself is 1. And then the common ratio is the base of our exponent, so that is 2. So our formula says S7, because we want the first 7 terms, is equal to 1 times 1 minus 2 to the 7th power, all divided by 1 minus 2. Now, since this is the first one we're doing, I'll simplify it by hand. But in general, we can just plug it into a calculator. So 2 to the 7th power is 128. So on the numerator, we have 1 minus 128. And in the denominator, we have 1 minus 2. Notice that this 1 that was our first term disappears because we're just multiplying by 1. It doesn't change anything. Then we end up with negative 127 all over negative 1, which gives us in total positive 127. Which, if we start with our first term and add all the way up to 7, is what we would obtain. For our second example, we can list A1, R, and N. So our first term is A1, so that's 4. Our common ratio is 0.3, and N is the number on top, which is 12. So we're going to have S12 is equal to 4 times 1 minus 0.3 to the power of 12, close parentheses, all divided by 1 minus 0.3. And so putting this in my calculator, I'll probably need an extra set of parentheses around my denominator. But once I do that, I have 4 times 1 minus 0.3 to the power of 12, close parentheses, divided by open parentheses 1 minus 0.3. And that gives me to 2 decimal places 4.12. 2 decimal places is sufficient. If you are going to put this into your calculator step by step, first with the numerator, then with the denominator, keep a few more decimal places so that you're able to minimize the rounding error that's involved. In addition to having our sums presented in sigma notation, we could also see them presented as lists of numbers. So evaluate the sum 2 minus 6 plus 8, and so on for n is equal to 13. So again, we need to identify in a new color A1, our common ratio, and n. Our first term is 2. To go from 2 to -6, we multiply by -3. To go from 6 to +18, we multiply -3. So a common ratio is -3, and n is equal to 13. So our sum, our 13th partial sum, is going to equal 2 times 1 minus -3 to the power of 13. Notice that I have an extra set of parentheses around the negative because I have to raise to the -3 to the power of 13 before it can be subtracted. All divided by 1 minus -3. So once again, I'm going to put this into my calculator. I have 2 times 1 minus, in parentheses, -3 to the power of 13, close my parentheses, divided by 1 plus 3, because we can simplify our numerator as 1 plus 3, which is equal to 4, if you'd rather put that into your calculator. And so this gives me the very large number, 797,162. And it makes sense that we would have a large number because every next number in the sequence, we're multiplying by 3. We might have numbers that we're subtracting because they're negative, but the next number that we add is going to be bigger than the number we just subtracted. So we end up with this very large number. Let's look at example B. So here we have A1 is equal to 4. It's the first term. R, well, it's times 2 times 2. And so R is equal to 2. That's our common ratio. And N is equal to 10. So now S of 10, the 10th partial sum, is going to be our first term, 4, times 1 minus 2 to the 10th power, all divided by 1 minus 2. So this is one that we could fairly easily evaluate by hand. But why evaluate by hand when we have calculators that can help us evaluate? And so putting this into my calculator, we get a still large but modestly smaller or more modest number, 4,092. This is much smaller, even though the other one has some negative terms that are being subtracted. This is much smaller because our numbers are growing much more slowly. We only double in size rather than triple in size every time. And it might only be a difference of 4 when we double 4 into 8, but then even that difference doubles when we get to 16. So that really shows us how we can use our formula even when we're given a list of numbers rather than the formula for the sequence. So the question I want to leave you with at the end of this first video is, infinite arithmetic series don't exist, but is it possible for infinite geometric series to exist? So think about that and then watch the next video in which we will discuss the answer.